Learning from self-labeled Twitter data by fast text with cost-sensitive sample selection bias correction. In this research, we are investigating methods for predicting a Twitter user's demographic information in an unbiased and efficient manner. In this presentation, we will focus on gender prediction. Due to Twitter's vast amount of free, public, and easily accessible data, it has become a popular research tool in recent years. Demographic information of data used in research is vital and necessary in order to make generalizations about a population. Because Twitter users don't need to specify things like their race or gender on their profiles when signing up, demographic information must be predicted. However, to do this requires a large amount of label data, which is costly and time-consuming to create. In the paper titled Simple Queries as Distant Labels for Predicting Gender on Twitter, Chris Emery and others propose a solution to the label data problem. They created a self-label dataset by querying tweets where users declare their genders. They then collected the entire timelines of the users whose initial tweets were queried. This method for labeling data generates a large amount of label data in a short amount of time. I will refer to this dataset as the self-label dataset. This is a seemingly good solution to the label data problem. However, we show that data generated in this manner is biased. In this context, this means that a model trained on the self-label dataset doesn't generalize well on the entire user population. Addressing bias in machine learning models is not very common, but can be extremely detrimental when left unchecked. It has been recently found that Google Voice has significant gender bias in recognizing human voices. This is upsetting to female users and could potentially endanger lives of female drivers and cars which use voice recognition. Emery and others train and test the fast text model on their self-label dataset and achieve state-of-the-art gender prediction accuracy results compared to other methods. The fast text model was developed by Facebook Research and is a text classification algorithm. It's a simple linear model which takes bag of n-gram input. The softmax function is used in the output layer to compute a probability distribution over the predefined classes. The fast text model is optimized by minimizing the negative log likelihood over the classes, where A and B are both unknown projection matrices learned by minimizing the loss function. The predicted probability that x sub I belongs to class J is computed using the softmax formula. In order to gain a better understanding for how the fast text model works and to be able to make necessary changes to the model in the future, I re-implemented the model from scratch in Python. To do this, I first had to mathematically derive the optimization solution for the weight matrix B and the weight matrix A. I then wrote a Python script to process textual data, which includes reading in each character and splitting them into the correct words. I then removed stop words and punctuation and then created the bag of n-gram instances. I then wrote the code for forward and backward propagation along with stochastic gradient descent. To assess whether the fast text model trained solely on the self-labeled dataset is biased or not, we tested the classification error on a random dataset which is representative of the general Twitter user population. We will refer to this as the manually labeled dataset. In order to make the format of this dataset correspond to the self-labeled dataset, I wrote a Python script which took each name in the dataset and collected that user's timeline. I then wrote a Python script which split each user into batches of 200 tweets with the corresponding label. We found the mean classification error on the self-labeled training set, self-labeled testing set, and the manually labeled dataset at each training epoch for 20 separate trials. This graph shows that the accuracy on the manually labeled dataset is very poor. The large discrepancy between the testing error on the self-labeled dataset and the testing error on the manually labeled dataset indicates that the model is biased. To reduce the bias in the fast text model created by sample selection bias, we propose to apply the kernel means matching method, or KMM. KMM is a popular method to correct the sample selection bias between a training set and a testing set. It learns to reweight training examples so that their sample mean is close to the sample mean of testing examples in a reproducing kernel Hilbert space. KMM is a non-parametric method which requires no assumption on the distribution of training or testing data. KMM finds an optimal set of weights or betas which minimizes the objective function. KMM restricts the range of betas so that they are non-negative but not too large. We propose 3 solutions to utilizing the KMM method within the fast text model to reduce sample selection bias. Our first proposed method is a weighted fast text model, which we call wFastText. We noticed that the self-labeled dataset had an uneven gender distribution with more female instances than male. Because of this, we propose 2 cost-sensitive solutions. Solution 2 is a weighted fast text model with cost-sensitive KMM, which we call wFastText CK. The third solution is a weighted fast text model with cost-sensitive fast text, which we call wFastText CF. The W-fastText model uses the correction weights learned by KMM to reweight the training examples. I rederived the optimization solutions for this model and implemented them in Python. This graph shows that W-fastText decreases the classification error when tested on the manually labeled dataset, but there's still a lot of improvement to be made. Our proposed W-fastText CK algorithm is the weighted fastText model with cost-sensitive KMM. This algorithm modifies the KMM component and turns it into a supervised learning method. When learning the reweighting coefficients or betas during KMM, we restrict the beta to a smaller range if the instance is female, but allow beta to lie in a broader range if the instance is male. This method improves the classification error when tested on the manually labeled dataset compared to all other methods, as seen in Table 1. Table 2 shows the percentage of males and females misclassified by each algorithm. The W-fastText CK has the most even amount of misclassifications between males and females, and misclassified more females than males compared to the fastText and W-fastText methods. W-fastText CF modifies the fastText component and directly reweights the betas when they are used to learn fastText. To balance the gender distribution, it assigns higher weights to male users and lower weights to female users. More specifically, W-fastText CF first learns the reweighting coefficients, or betas, by solving standard KMM, and then it reweights each beta depending on if the instance is male or female. The classification results on the manually labeled dataset under the W-fastText CF method are better than both the original fastText method and the W-fastText method. However, they are worse than the W-fastText CK method. In this research, we proposed 3 solutions to correct for the bias in the model created by data which is not representative of the entire user population. Our solutions are able to leverage the efficiency of the self-labeled data, but in an unbiased manner. Our methods give higher accuracy results when testing on new data which is representative of the entire user population of Twitter while utilizing self-labeled data during training.